So today we'll talk about the semantics of predicate logic, introduce the idea of a model, and show how to evaluate propositions relative to a particular model. Now, it's actually very important that you remember your truth tables from propositional logic. You need to be able to look at woofs in propositional logic and be able to state their truth conditions in any given case in order to get much value out of this lecture. So the semantics of a language are the rules for evaluating the truth and falsity of the propositions that we can formulate within the language. In logic, we think of the truth conditions of a language as constitutive of the meaning of the propositions. So in propositional logic, you'll remember we did this with truth tables, and as I just said, truth tables, our understanding of truth tables figures critically in our ability to do the semantics of predicate logic, but we actually can't use truth tables themselves to evaluate predicate logic statements. In propositional logic, we know that the woofs all have specific truth values that are determined by their constituent propositions. So, for example, if you have a proposition like if P, then Q, or R and S, you know that the truth value of this proposition is a function of the truth values of each of the constituent propositions. So you know, for example, that the main operator here is OR, right? And so you know that if this is true or this is true, the whole statement is true because you know the truth table for OR. And you know that each of these constituent propositions, the truth values are determined by their constituent propositions in the truth table for these operators, right? So that's just all old hat. So that's what we mean by truth functionality. But in predicate logic, because we've introduced quantifiers and variables, we now have expressions that do not have specific truth values. So the proposition FA will have a specific truth value, but FX does not. And that's because we've introduced a variable. Now you'll notice I didn't call FX a woof. I called it an expression because this isn't a woof, but it is because of the introduction of variables and quantifiers that we can't use truth tables to do the semantics of predicate logic. So you'll remember that in a previous lecture we explained that the universal quantifier is essentially an infinite conjunction, and the existential quantifier is essentially an infinite disjunction. So for example, if we take F to mean funny, then the proposition that everything is funny for all x fx would have to be converted into its propositional logic equivalent. And if everything is meant to range over the entire universe for all time, then this would actually have to be an infinite conjunction. So another way to understand why we can't use truth tables in predicate logic is that we would need infinitely long truth tables. And we don't have the ability to do that since we are finite beings. We also noted earlier, and I'll just remind you of this because it's cool, that this leap to infinity gives predicate logic in all the more powerful languages all sorts of interesting and rather weird and spooky properties. For example, predicate logic is what we call undecidable, meaning that there can be no purely mechanical method for determining whether an argument in predicate logic is valid or invalid. there are, I say here, like truth tables or truth trees. There are truth trees in predicate logic, but there is a truth tree system for them, but it's not purely mechanical. You're not guaranteed to determine whether something is valid or invalid simply by applying the rules. All right, so let's talk about models. The semantics of predicate logic makes use of these, and they're actually a very simple idea. All models have three distinct parts. One is that it specifies a universe of discourse. Now, a universe of discourse is essentially just a set of objects that we're talking about. So we could say our universe of discourse is numbers, or our universe of discourse is people or bugs. It really doesn't matter what it is, or it could be something very specific. In the past, we've talked about, say, a universe with only 3 objects, and we can do that too. And then what it does is it specifies an interpretation of the names and also the predicates in this universe. So the best way to understand this is just to do one. So here's a fully specified model. And this is similar to the one that's actually in your book. So let's just say that our universe is cities in California. And we're going to name a few of these cities. So little s is Sacramento, F equals San Francisco, L equals Los Angeles. Now, importantly, when we say that the universe is cities in California, we mean all the cities in California, not just the ones we've given names for. And that comes up later as an issue. And then we'll go ahead and just specify some predicates. So S equals, this is the way it's actually stated formally, the relation that holds when X is south of Y, basically just means south of. P means more populated than. X is more populated than Y. So these two here are relations, or binary predicates, two-place predicates. And then we identify one-place predicate, which is the class of objects that are capital cities. So Sacramento is the only one, obviously, if you know your California cities. Okay, so now let's go ahead and evaluate some propositions within this model. I've gone ahead and summarized the model in the yellow box up on the right. So is capital P little s little l true in the model? Go ahead and each time I give you an example, of course, you should stop the video and figure this out for yourself. So capital P little s little l says that Sacramento is more populated than Los Angeles. Well, clearly that's false. Capital C little s, this says that Sacramento is the capital, which of course is true. This says that Los Angeles is to the south of San Francisco and Sacramento is to the south of San Francisco, which is false because one of these is false, right? So here you see that you have to really know your truth tables to be able to evaluate propositions that start to use the operators. Okay, is this true in the model? Los Angeles is to the south of San Francisco. Well, that's true. And since this is a disjunction, we don't even need to evaluate the second one. So this is true. If Sacramento is more populated than Los Angeles, then whatever, because Sacramento is not more populated than Los Angeles, so this is false, so the conditional is true. Again, this is the kind of reasoning you need to be able to do intuitively. Either it's not the case that Los Angeles is the capital or San Francisco is the capital. Well, that's true. Neither one of these is the capital, so the whole statement is true. Okay? So you'll notice, of course, that these are predicate logic expressions that don't contain any quantifiers. So let's go ahead and ratchet it up a little bit and put in some quantifiers now. There exists an x, c of x. There is something that is the capital. Well, yes, indeed, that would be Sacramento. So true. Everything is the capital. False. There exists an x such that x is the capital, and there exists a y such that x is more populated than y. Well, Sacramento is not more populated than Los Angeles, and it's not more populated than San Francisco. Actually, I'm not sure about that, but let me just say that. But there's all sorts of other cities not named that Sacramento is more populated than. So this turns out to be true. We have to think about cities or objects not in the model to evaluate that. For all x, either x is the capital or there exists a y such that x is more populated than y. Well, that's actually not true. Now, I'm not sure what the smallest bona fide city in California is, but it's not Sacramento. So if you think about the smallest city in Sacramento, that is not the capital, and there is nothing that it is more populated than. So that would be an instance of something for which this is not true. And since it says everything has this property, this turns out to be false. There exists an x and there exists a y such that x is more populated than y and x is to the south of y. Well, surely, Los Angeles is more populated than San Francisco, and Los Angeles is to the south of San Francisco. It is not the case that for all x, x is more populated than s. Well, that says it's not the case that everything is more populated than Sacramento, and that's certainly true. There are many, many cities that are less populated than Sacramento. Okay? So we've just been evaluating some simple sentences, but we haven't been, but what we've been doing is just saying whether they're true or false and giving some reasoning to support this. But it's important to understand what's really involved in doing a full evaluation in predicate logic. So think about this proposition. For all x, if c of x, then there exists a y such that y is to the south of x. So that says for everything, if it's the capital, then there is something that is to the south of it. So surely that's true because there's only one thing that's the capital, which is to say Sacramento, and there are many cities, including San Francisco and Los Angeles, which are to the south of Sacramento. So it's pretty easy to determine this is true. But when you're doing a full evaluation, you actually have to consider very explicitly all the ways that this sentence can be true or false. So this is what a full evaluation, a full metalinguistic evaluation of this sentence will look like. So let's see if we can understand what this says. It says, the wolf, meaning this up here, is true in the model if every substitution of a city name for A, now A, notice, is italicized here. So what that means is that we're using the meta language. It's a way of referring to any name whatsoever, right? So the if is true in the model if every substitution of a city name for A. In the proposition, if CA then SBA, results in a true formula for at least one substitution of a city name for B. Again, metalinguistic B, some name. So what's that saying? Well, what it's saying is that this whole statement up here is going to be true. If any name that you put in for X, because this says for all X, right? And the universal quantifier is binding the X. So if for any name at all that you put in for X, there is some name that you can put in for Y, some one name, it only has to be one, that will make the whole statement true. That's what it's saying. Now, after that, it gets a little easier. Now, there's only one capital city. So every substitution of a city name other than S for A will result in a false antecedent, making the conditional true. In other words, if we substitute anything but S in for X, or if you look down here, right, if you substitute anything, if A is anything but S, then C of A is going to be false, right? So suppose it was L. Well, Los Angeles is not the capital. Suppose it were F. Well, San Francisco is not the capital. So if you make the conditional, the antecedent of the conditional false, then we know the whole conditional is true. Okay? So anything that's not Sacramento makes the conditional true. But if we put Sacramento in, which is the only remaining consideration, then if we put Sacramento in for A, then of course it's true. And then we'll say, then there exists something. We have to find a B now that is south of Sacramento. Well, of course, Los Angeles, San Francisco, and plenty of others. Okay? So to review, there's only one capital city, so every substitution of a city name other than S for A will result in a false antecedent, making the conditional true. But when S is substituted for A, then the proposition is true if there is at least one substitution of a city name for B that makes the conditional true. So, for example, we could substitute F for B, that makes the consequent true, and thus the entire conditional true. So that is why this whole thing is true. That is the full metalinguistic analysis. Now, full evaluations are even a little more involved when we're required to think about objects that are not named in the model. In the previous one, we didn't have to. And in order to do that, well, think about something like this. It's not the case that there exists an X such that X is south of L. So there is nothing that is south of Los Angeles. Well, Sacramento is not south of Los Angeles, and San Francisco is not south of Los Angeles. So as far as cities named in the model, nothing is south of Los Angeles, but there are many cities that are, not a ton, but there's many cities that are south of Los Angeles, and they're just not named in the model. So San Diego, for example, would count here. So it's not the case that there exists an X such that X is to the south of Los Angeles. Well, actually, no, that's false because San Diego, not mentioned in the model, is south of Los Angeles. So in order to do a full evaluation of something like this, we actually need a new term. We'll follow the text here, as we always try to do. The text talks about what they call an A variant. Okay, so all an A variant is something a name of an object that is not explicitly named in the model. So in order to evaluate, it's not the case that there exists an X such that XSL, we need to be able to talk about A variance. So here's the straight up evaluation of it's not the case that there exists an SXL. So it's not the case that there is something that is to the south of Los Angeles. So what does it say? It says the wolf is true in the model if the proposition SAL, A being the metalinguistic A, referring to anything whatsoever in the model, SAL is false for every A, and also every A variant, which we just defined. Okay, why false? Well, look at the negation, right? This says it's not the case that there exists an X such that X is to the south of Los Angeles. So what this is saying is that for any name that we put in for this expression, any name that we put in here, any A that we put in for the X, that has to be false in order for this whole statement to be true, right? So that's just the nature of the negation, right? If we say not P is true only if P is false. So this whole statement is going to be true only if SAL is false for any A that we stick in for X, and also any A variant. Well, then it just goes on to point out that, look, SAL is false for every A specified in the model. After all, right, if you look at the model, we have three names: Sacramento, San Francisco, and Los Angeles. And if we say Sacramento is to the south of Los Angeles, we get a false statement. If we say San Francisco is to the south of Los Angeles, we get a false statement. If we say Los Angeles is to the south of Los Angeles, we get a false statement. So for any A that we can stick in there, SAL is false. So it's not the case that the SAL, it's not the case that all of those turns out to be true. Okay, so far it's true. But then we have to think about every A variant, and that's going to be all the other cities in California. So if we choose one judiciously, such as, for example, San Diego, right? What if we put San Diego in there? It's not the case that San Diego is south of Los Angeles. No, that is actually true, making this false. So all we needed was to find one, because this is telling us there isn't one. Okay? So SDL is true in the model, making the wolf, it's not the case that there exists an X, SXL, false. Now, if you're a normal person, you found that confusing, just like the previous one. And it is, in fact, very tedious. It's important to spend the time to work through it to make sure that you do understand it. But in reality, we are not in this class going to be producing analyses like these. What we are going to be doing is learning how to evaluate models and really sharpening our ability to understand predicate logic sentences. So what we'll do for the remainder of this video is work on a simple model, which I've drawn right here. So this is a universe. The universe is defined as shapes in the box to the left. Now, the box itself is not part of the universe. It's just these shapes. So A is the name of the blue circle. B is the name of the red square. D is the name of the blue triangle. And C is the name of the green star. We have several predicates: red, blue, green, triangular, circular, square, and star shape. These are one-place predicates, sometimes called properties. And then we have two-place predicates, just two-place predicates within, so we can say A is within B, or and also left of, so we could say A is to the left of B. And notice that when we say left of, we mean completely to the left of. So for example, part of D is to the left of C, but not all of it. So D is not to the left of C, A is not to the left of B. All right, so let's go ahead and do some study questions. Now we'll do this silently, but I give you the answer with a little bit of an explanation after each one, but go ahead and approach these the way you normally would, by stopping the video and then moving it along to see if you got the right answer. And also, if you don't have a intuitive grasp of the truth conditions of these sentences, of the truth functional operators, scurry back there and get those back in your memory before you do this, or this is just going to really be a waste of your time. Okay?